come to a very important result, which is the density of states for a free particle. We'll use it over and over again in the book. Often you'll see this result derived based on the results just obtained for a particle in a box, but clearly a free particle is not a particle in a box, and it has an exponential or a cosinusoidally oscillating plane wave solution and not a stationary sine wave solution as just derived for a particle in a box. So we'll stick to our e to the ikx solution, but we will derive our result using the concept of periodic boundary conditions. In essence, the idea of periodic boundary conditions is that a wave function must eventually repeat its value as we go to a very large distance. We can choose to go to infinity and say that psi of 0 is equal to psi at infinity, or we could imagine taking a system and bending it ever so slightly on the atomic scale, but enough so that eventually the system returns to meet itself, and then at this point, after a distance L, we have psi of 0 and psi of L being equal to one another. Now this sounds like an artificial construct, but what we will see when we use this result is the value of L we choose turns out to be unimportant in determining the numerical values that we calculate with the formula we're about to obtain. So the requirement then that the wave function for a free particle at x equal L be equal to the wave function at x equals 0 is this. And this is satisfied then because e to the ikx is cos kx plus I sin kx is satisfied with the following constraint on the wave number. Similarly, in the y and z directions, notice now we have in this three-dimensional problem 3 sets of integers describing each state of the particle. These are called quantum numbers. For the particle in a box we just looked at in 1 dimension, there was one quantum number, n. For this free particle in 3 dimensions, we now have 3 quantum numbers, nx, ny, and nz. Now, if we write down the kinetic energy of the particle using the result that E equals h bar k squared over 2m, where in 3 dimensions k squared is kx squared plus ky squared plus kz squared, we can see that the energy is calculated directly once the values of kx, ky, and kz are known. There is an interesting way of looking at the distribution of k points. The spacing between adjacent k points in any direction, for example along the x-axis, is given by the distance between the points for successive values of the integer nx, nx equal 10 and 11 say, and that distance is 2 pi over L. So these points in k-space, in this case this is the x direction, are equally spaced in 2 pi over L. Of course, as L goes to infinity, the spacing between the points goes to 0, and space is then filled with a mesh of allowed k points, which may be arbitrarily close together in an infinite space, lying on a square grid and separated from one another in x, y, and z by a distance 2 pi over L. So here is a picture of k-space filled with a mesh of the allowed k values. And the non-trivial result comes when we ask how many states are there between a point k and k plus dk. Now this is an isotropic space, so the value of k, kx squared plus ky squared plus kz squared, can be described by a line pointing out from the origin and touching a sphere of radius k. So the volume between k and dk is simply given by the area of the sphere So that's the volume of k square space between k and dk. And the number of states in that will be given by the volume of any one state. Well, the volume of any one state is simply a little cube of sides 2 pi over L. And so the volume of the cube in k space, and this is where we're working, is simply the sides of the cube multiplied together, or 8 pi cubed over L cubed, which is 8 pi cubed over the volume that we're considering. And so the number of states in this shell then is given by this expression. So, simplifying a little then, we see that the number of states between k and k plus dk, which I guess I can write as dn dk, is given by v k squared over 2 pi squared. Now, the quantity v appears in this expression, and of course it must, because our periodic boundary conditions were quite arbitrary, and v will go to infinity as the element goes to infinity, but we used it as a calculational device to obtain the result that the number of states per unit k varies as k squared, and this is an extremely important quantum mechanical result. In the book you will find similar results derived for 2 and 1 dimension. Please go look at them, we'll use them, and you'll see that the v or the a in 2 dimensions or the L in 1 dimension will drop out of the final calculated quantities.